Okay, well, let me kick off. I'm Matt Rostron. I'm the Deputy Lab Director of Microsoft Research in Cambridge, and it's my pleasure today to welcome you to this Optics for the Cloud PhD event. Um, it was about 3 years ago, or 4 years ago even, I think, when we started talking about this internally, and we said, we're extremely interested in how optics could revolutionize the cloud for optical networking, storage, and compute. And we were very keen to engage with the larger academic community. And we pulled this together as a mechanism, this Optics of the Cloud Research Alliance, as a mechanism to allow us to interact and to sort of be involved with the community. Initially, sort of very much in the UK and then in Europe. And more recently, I know we have people involved who are also in UCSB and places like this. So we've really expanded up. So it gives me a great pleasure to welcome you. This is our PhD event. This is the first virtual event for the Optics of the Cloud Research Alliance. It's also, I think, for Microsoft Research, one of the first virtual events that we've done. So we're all learning. I hope that you enjoy what we have today. Can I go to the next slide, please? So, putting a day together like this, whether it's in person or virtually, of work. I'd really like to thank all of the people involved. On the sort of the scientific chair side, we have James and Francesca. And I think Francesca, you're doing today, and James may be doing tomorrow. We have a number of speakers also who have also been heavily involved from the Microsoft side in putting all this together. Hitesh, Pablo, and Paolo. We have the team that's sort of done all the logistics and organization. Scarlett, Claire, and Lynn, and I'd like to thank you all. And also Ben has also been instrumental in pulling all of this together, getting the program ready, and making sure that we have a good set of talks for these next sort of 2 afternoons. Can I go to the next slide? So today's agenda starts off with me welcoming you, which I've almost completed. Hitesh will be giving you a sort of a whirlwind tour of optics to the cloud. I've seen the number of slides he's got. It certainly will be whirlwind as we go through them. And then we're going to go into a number of talks from the PhD students. Now, all of these PhD students are special because they're all funded with or by Microsoft. And we have people internally inside Microsoft who work very closely with their academic mentors and advisors in order to help make the work and help to input on the work, which to me is a great thing. I often say that Microsoft Research isn't a funding body. We're not like the EPSRC in the UK or the NSF. We don't just write checks and that's it. We like to actually be involved and we like to partner. And so it's great to see these talks happening and people from both sides, from the universities as well as from Microsoft, involved in them. So that really brings me towards the end of what I want to say. Can I go to the next slide, please? It sort of falls to me as well to to sort of give you some of the housekeeping, some of the thinking for how we would like today to operate. I can tell you, having done other things online, that if everyone is completely silent, it's not great. We have chat windows, so you can ask questions in the chat windows, and there are not just the speaker, but there are others online who are going to be able to answer questions. And I would encourage those from Microsoft and those from the universities, if you see questions coming in where you think you can help answer them for the speakers, you should dive in and provide some of the answers. Get a little bit of sort of almost interactive discussion happening in the talk associated with the event. If you'd like to ask questions, I think certainly inside the Microsoft ones, they're all going to be live. So you're able to raise your hand. That will attract the attention of the session chair. Today is Francesca. Or you can send a message in the meeting chat. Some of the talks are recorded, so obviously it's not going to be possible to stop them in the middle to answer questions. For the live ones, if you've got something that you think is really important to be answered, you should just ask it and put your hand up and make it interactive. We should also, I think for all these talks, it's a great opportunity to collect feedback. If you have thoughts or comments that you would like to share, please feel free to share them with the speakers, either through email or through going through us after the event. Can I ask everyone to stay muted? I think we've all noticed this tendency in some of these online meetings for background noise and whatnot to come through. And obviously, if you're trying to talk and there's a lot of background buzzing and hissing coming through, it's a lot of distraction. So let's please turn those off, of course, unless you want to speak. And I would encourage people, if they're going to ask questions, to actually switch the camera on. I think it makes a huge difference in these online meetings if people have their cameras on when they're interacting. We have the raise the hand again, which I've just mentioned. And, Claire Morgan, who is online, and we've got an email address for her here. If you're having technical problems, please feel free to send her an email and we'll do what we can to sort it out. Obviously, with these sort of things, it's not always possible to sort out the problems remotely. I've discovered that my house bandwidth is a real problem. So I'm looking forward to some of the optical networking talks to understand what we're going to do to sort the bandwidth to my house out. But anyway, so let me just conclude this bit by saying, please try to be interactive. Don't just think of this as I'm going to sit here for a few hours and just listen. Try to think, ask questions, be involved. That would be the basic message. So I think that's my last slide. Scarlett, can you just go to the next slide? Is there another slide?
No, I'm going to hand over to Hitesh now.
Okay, so I'll hand over to Hitesh then. So here we go. So Hitesh is our first speaker. He's going to give us a talk, a whirlwind tour of optics to the cloud here at Microsoft. And Hitesh has been with us for many years. I think coming up to 12 years or 14 years, is it, Hitesh?
It's not 12, and it's barely
is it not?
10.
Is it barely 10? You're a youngster. Is one of the key people, one of the key leads on all of our optics to the cloud work. So I'd like to hand over to him. And Hitesh, the floor is yours.
Thank you, Ant. Scarlett is giving me control. Just can I do a quick audio check? Ant or Francesca, could you just say, perfect, excellent, thank you. So it's great to see so many people here. Thanks, Ant. Thanks everyone for your time. And what I want to do over the next 15 minutes, as Ant mentioned, was give you a taste of some of the work happening here at Microsoft Research as we push these optical technologies for the cloud. And I mentioned this in the past. Give me a second. It will just take me a second to get control.
You should have control, Hitesh.
Yeah, Scarlett, it just takes 10 seconds. That was interesting.
Yeah, it was.
Was a very nice talk, Hitesh. Thank you very much.
I knew that. Well, as Ant mentioned, it was a whirlwind tour. Apologies for this. We're learning on the fly. Just give us a second, please. Thanks, Scarlett. Let's try this again. So again, this takes 10 seconds, but I'll get started in the meanwhile. Hopefully I'll get control of being able to move the slides. So, and something that I've mentioned in the past is that we're really worried about the fact that almost all technologies underlying our cloud infrastructure seem to be approaching the tail end of their exponential growth phase. This applies to compute, it applies to networking, and if the slide moved, you'd see that it would apply to storage too. And so what we're really looking for is, can we leverage bleeding edge optical technologies that could lead to new growth curves in the post-Moore's Law era? And you'll see this as a common theme as across the projects as I talk about them. So I'll start on the storage front. And one of our big projects in this space is Silica. So this is a collaboration with Azure Storage. And what we are trying to do is see if we can disrupt the archival storage space. The motivation is simple. The amount of data in the cloud just keeps growing and growing. And most of this data is archival in nature. I'm sure all of us have thousands of photographs of cats and dogs and babies, personal records and financial information, astronomical data, weather data. And today, all this is stored in archival storage, spools of tape. However, this technology is finding it hard to continue scaling. Not to mention, even with these technologies, data needs to be copied every 5 years in order to avoid bit rot, which means high cost and high complexity. So the aim in silica is, can we use glass or silica as a storage media in order to reduce or eliminate this gap? Now, the underlying technology that enables this work is femtosecond lasers. And the basic concept was developed at the University of Southampton. The idea actually, you shine this laser on a piece of glass, and at its focal point, we get a nano grating or a voxel. By changing the intensity of the laser and by changing its polarization, we can change the size and the orientation of the voxel, hence allowing us to put multiple bits on each voxel. And can create layers of these voxels, essentially getting a three-dimensional high-density storage medium. The other advantage of this technology is that it allows us to separate the write technology from the read heads. So the reading in this case is done using computer-controlled microscopy. We shine a polarized beam of light that can be moved along the XY axis, and we can change the focal plane. And this received light is then decoded using machine learning, which in turn allows us to achieve higher density as opposed to traditional techniques. Now, one of the key advantages of using glass as a storage media is its amazing durability, thousands of years. So we've boiled our samples, we've magnetized them, we have scrubbed them, we have microwaved them, and we have baked them. And in all cases, not only did the sample survive, but we were always able to recover the entire data set. Now, this is something that got us really excited, and it led to external collaborations. For example, we have a big collaboration with Warner Brothers. And as you can imagine, they have lots of high value archival data to store. Tons of movies of cultural importance, which today are stored in these spools of archival tape in temperature-controlled, expensive data warehouses. So we worked with them to write the original 1978 Superman movie on a piece of glass, which was actually showcased in Satya's keynote at the end of last year, so our CEO. It's a small piece of glass, 75 millimeters by 75 millimeters, so like a coaster. We wrote around 76 gigabytes of data plus some redundancy information across 74 layers in this glass. And this was at the end of last year. Our density information or our density status has improved significantly since. Now, this is obviously an achievement that we are proud of. It led to advertisement for the company. It allowed us to have this collaboration with partners who have high value archival data and who are willing to work with an experimental futuristic technology. But there's a meta point I want to make here regarding the journey from the optics to the cloud. So in this case, the building block technology is femtosecond lasers. Amazing piece of technology developed in a physics lab over a decade. However, it's still a long, long way from what I'd call an end-to-end storage system. Because a storage system like that needs to have a full-blown write pipeline. It needs to have a glass library. It needs to have a read pipeline. And this entire system needs to be designed with high throughput, high capacity, fault tolerance, and of course, it needs to be coupled with a cloud storage software stack. And this is exactly what the team has been working on over the past 2-3 years. And I think the main reason we've been able to answer this feasibility question in the affirmative is because of the cross-layered nature of the team. So we have hardware architects, software engineers, physicists, and chemical engineers working in the same team in the same labs. And this is a point that Pablo will make in his talk tomorrow, how we are now looking at ideas from the networking domain that could improve our read and decoding technologies even further. Of course, not all the technical questions have been answered. We've gone from this basic feasibility mode, can we do it, to the should we do it, getting this technology ready for prime time, which has both technical questions to be answered, but also strategic questions to be answered. So the next thing I want to talk about is in the networking space, and this is a project called Sirius. And the idea or the motivation here is similar. Historically, we've relied on this exponential growth or the free scaling of electrical packet switches, which has been great, but things are looking gloomier and gloomier. And so the question we are asking is, can we use optics to generate a new switching growth curve? Now, there are many switching technologies, optical switching technologies out there. Some of them have been explored by people in the audience for many years. And actually, this is a question that the community has been asking as a holy grail for the past 15, 20 years. The particular technology we pursued is actually very simple. It's a grading a piece of glass with etchings or an EWGR. So if I want to speak to Francesca, I'll send my data on the green wavelength. And if I want to speak to Scarlett, I'll send my data on the red wavelength. So we can use this as a switching technology in our data centers by coupling it with a tunable laser. However, in order to support bursty cloud workloads, we need to be able to switch in a very fast fashion, nanosecond granularity, which means a tunable laser that can tune its wavelength in a very fast fashion. Since this is hard to do with existing off-the-shelf tunable lasers, we took the dive in the fabrication space and we designed our own custom PIC that can tune over the entire optical C-band in less than a nanosecond. And we have multiple implementations and multiple variants of this design. Now, from a chip perspective and from a technical perspective, this is something that I think is very neat, and I understand I'm biased. It was a great learning curve to go through this fabrication exercise. However, I want to go back to my meta point. This is a very useful building block, but it's still miles away from an end-to-end system, a cloud network offering nanosecond switching at end-to-end granularity. And in order to get there, we had to solve several hard systems challenges at different layers of the cloud network stack. So just to give you an example, the EWGRs mentioned and the tunable lasers have around 100 wavelengths. So we can use this technology easily to connect 100 servers, but in a data center, we need to connect 100,000 servers. So how do we scale? So we had to solve all these questions in order to build a prototype that can offer nanosecond granularity switching from an application perspective. And Paolo will describe in his talk tomorrow as to how we got there. And I think the secret sauce was the fact that we didn't go after these problems in a layer by layer fashion with point solutions. We actually came up with a cross-layer design, which means the solutions are practical and we think deployable. However, there's still a long way to go. We moved from can we do it phase to the should we do it phase. We understand the design space. We understand the trade-offs that different solutions bring to the table. And now we are trying to identify the best cloud scenarios where this technology makes more sense. So that was the work in the networking space. And like storage, this is stuff that has been happening over the past 3, maybe even 4 years. So the next thing I want to talk about is something completely fresh off the press, compute. The motivation again is simple. Moore's law is slowing down, and can we use optics for compute acceleration? Now, I'm sure most of you have thought about how optics can be used for different computational primitives. Just as a simple example, if I were to take an image in an optical domain and I shine it through a lens, on the focal plane, I get the image in the Fourier domain, which can be used for things like pattern matching. Similarly, if we wanted to do vector by matrix multiplication, we can represent the vector by an array of pixels. We can have our matrix on a spatial light modulator. And on the output side, on an array of cameras or photodetectors, we get the dot product of the vector and the matrix. Pretty well-known concepts. However, there are 3 things I want to point out here. First, this is analog computation. So the precision is limited as compared to a digital counterpart. Second, the computation here is free once you're in the optical domain, but it does require us to go from the digital data to the optical domain and then back. And finally, I want to reiterate that we are not talking about general purpose computation. We are talking about acceleration of specific computational primitives. So we could imagine using these as an optical coprocessor or an optical accelerator. So imagine using this optics for accelerating AI inference workloads. In this case, we have an image of a car, which is processed by a digital engine, which is implementing some parts of a new neural network. It's converted to the analog domain, and then we invoke our optical accelerator to do our vector to matrix multiplication. And finally, we go back to the digital domain with the answer saying, well, this is very likely a car. Now, this is an interesting pipeline, but if you notice, every time we invoke the optical accelerator, we need to take the tax of the digital to analog and analog to digital conversion. And by the time we account for the power and the cost and the complexity of those conversions, most of the benefits here seem to go away. So even though there's a lot of hype regarding the use of optics for accelerating AI inference, when you look into the gory details, the benefits are not that spectacular. However, we don't think this is a dead end. There are other computational models where the pipeline is different. For example, if you look at solvers for combinatorial optimization problems, which are prevalent in when you're doing finance portfolio optimization or you're doing molecular drug discovery. So in this case, we have an optimization problem. It's converted into the analog domain, and we invoke the optical accelerator hundreds of thousands or tens of thousands of times, and we iterate to the optimal solution. And once we get close enough, we go back to the digital domain. So this is an application scenario where optics can really shine because the overhead of the digital to analog and analog to digital conversion is amortized across many computations. So this is a particular computational model that we are excited about and that we are pushing on. However, it's early days. We are still in the can we do it phase, and hopefully we can come back in a year or two and answer that question in the affirmative. So to step back and summarize, we are genuinely worried about the fact that compute, networking, and storage seem to be approaching a plateau. And we've taken this bet on developing optical technologies that could lead to new growth curves. And we really believe that this cross-layer interaction and cross-layer techniques are going to be the key to success on this journey for us. So thank you all for your time. Hopefully that was useful. Happy to take questions verbally on the chat window, over email. I'm here for the next couple of days. Hopefully everyone has a good workshop. Thank you. Francesca, I don't know how we are doing on time. Do we have time for a few questions, if possible?
Yes, I think we would have time for a couple of questions if there are.
Any brave question speakers? I see somebody unmuted.
Yeah, so there is Thomas Gerard, please. Thank you.
Hi, Tom.
Hey, Dash. Thanks for your talk. You spoke about whether the optical switching solution is if you should do it for the cloud data center. That's the work stage you're at now. And I'm wondering what other kind of application spaces it might be suitable for and where you think it has a lot of opportunity.
Yeah, so this is a point, excellent question, Tom. So I'll give you the sort of the 30-second answer, and I believe Paulo will later today will elaborate on this. So there are different kinds of workloads where optic switchings may or may not shine. So just to give you a concrete example, if you think about how we think about servers in data centers, they have a bandwidth requirement of around 50 gigs, 100 gigs. So if you are trying to connect optical switching for those sort of scenarios, it provides benefits, but it's not as compelling because the electrical switches are doing a pretty reasonable job. On the other hand, there are many scenarios like AI scenarios where these digital AI chips have a bandwidth of hundreds of gigs. Actually, the latest NVIDIA GPUs have around 2.4 terabits. When you start thinking about the kind of switching requirements, both from a power and a cost perspective for, let's say, AI training and AI inference, that's where optical switching may really shine. So that was sort of the meta context behind that comment about scenarios. We really need to think about the bandwidth, the latency, and other requirements, and of course, things like deployability in order to identify where this technology may or may not shine. And I think this is a point that Paulo will make in his talk. I saw him, so maybe he can comment on this.
Yeah, no, I just wanted to add that latency is also the other dimension, and that is very important, which for traditional traffic, where is VM to VM, most of the latency goes into the stack. So reducing, from, microseconds to nanoseconds doesn't really matter. But once you start going for some of the more aggressive workloads, like resource disaggregation or memory disaggregation, then latency start, becoming like a primary bottleneck. And so the ability effectively of having, a solution that can give you ultra low latency becomes very compelling.
Thanks, guys.
Other questions? So Pashmina had a comment that yes, so Pashmina says that the kind of comments being made regarding optical computation would be good for any iterative algorithms, as long as one can evaluate the goodness in the optical domain, not just combinatorial optimization. Pashmina, that's a spot on comment. Yes, it was actually the general comment there was about if your computational pipeline looks like this, that you can remain in the optical domain as long as possible, and hence amortize the overhead of the D to A and the A to D. Those are the scenarios. And yes, we should have internal discussions and external discussions on the kind of application domains where this computational model holds.
Fantastic. I don't see any further question for Hitesh, but please feel free to keep using the meeting chat for any further question that you may have for him. But without further delay, I would also like now to introduce the next 4 or so exciting talks from PhD students who are collaborating with us, and we will then conclude the day with the last Microsoft talk. So without further delay, I would like to introduce you the first speaker, Arslan Raja. Arslan is a member of the Laboratory of Photonics and Quantum Measurement Group at EPFL, under the supervision of Professor Tobias Kippenberg. He works on photonics integrated multi-wavelength sources for data centers. Actually, Arslan joined us for an internship with us last summer, working on Project Sirius under the supervision of Sophie Lange. And today his talk is about sub-nanosecond optical switching using multi-wavelength sources based on Soliton Microcomb. So let's start his pre-recorded talk, and this will be followed by question and answer, where Arslan will be there to answer any question that you may have live. So thank you.
Good afternoon, everyone. My name is Arslan Sajid Raja, and I'm a PhD student in the lab of Professor Tobias Kippenberg at EPFL. This work is done in a collaboration with Optics for the Cloud team at Microsoft Research, Cambridge. Today, I will talk about sub-nanosecond optical circuit switching using Soliton Microcomb. Soliton Microcomb is a multi-wavelength source, or alternatively, it can be considered as emission of multiple lasers from a nonlinear element, which is microresonator, a circular device shown on this photonic chip. I want to start my presentation by giving the motivation of our work. This figure shows the multi-tier architecture of current data center, in which servers are interconnected with the help of electronic switches and optical fiber. The black line represents optical fiber in this figure. The data is converted from electrical domain into optical domain and from optical domain into electrical domain using optical transceivers. The conversion process adds some overhead, and also these devices are power hungry. Due to the massive flow of data within the data center and also to the external world, causes a lot of issues related to the power and scaling. One of the main reasons behind all these issues is following. All the electronic components used within the data center are reaching the performance limit. In order to solve all these issues, wavelength-based circuit switching is proposed as a key enabling technology. This particular method is used by our collaborator at Microsoft Research, Cambridge. The basic idea behind this method is following. The interconnection between two servers is only established using a predefined color of the light. For example, if this server wants to talk to this last server, they can only establish a link or communicate data using green color of the light. Some advantages of this particular technologies are following. There is no need of optical to electrical and electrical to optical conversion, which means there will be less number of optical transceiver used in the data center and hence more power efficient data centers. The interconnection between servers within the data center are more efficient as compared to the conventional data center. This particular property is more important for certain applications such as cloud computing. The port scalability is not an issue as most of the technology or method can be relied on a photonic chip-based platform. One of the key components required for optical circuit switching is a multi-wavelength source. A multi-wavelength source can emit many colors of the light. A straightforward and ideal solution is to use tunable laser. A tunable laser can emit many colors of the light either by changing the temperature or current applied to this particular laser. It has been demonstrated that this particular laser cannot tune faster than 5 nanoseconds. And in order to efficiently utilize the different resources within the data center, it is important to switch at sub-nanosecond time scale. Later, it was proposed that an additional element known as wavelength selector can be used to select different color of the light coming out of multi-wavelength source. This particular technology has enabled sub-nanosecond time scale circuit switching. In order to understand this thing in more depth, let's consider we have a 3 laser diode, red, yellow, and blue, and they're continuously emitting the different color of the light. In order to select one of these colors, we will use optical switching element, semiconductor optical amplifier. If we want to transmit the red color, we will apply a control signal on the first SOA. By applying the control signal on first SOA, we'll see that this red color is transmitted. Now, if we want to switch from red to yellow, we will apply a control signal on the next SOA. So by applying a control signal on the second SOA, we start transmitting the yellow color of the light. Similarly, if we want to transmit the blue, we will apply a control signal on the third SOA. So by applying the control signal on the SOA, we can select one of the color emitting from the laser diode. This particular method has already enabled sub-nanosecond timescale circuit switching. For example, now if we want to increase the number of channels, then a simple solution is to use array of the laser. For example, if we want to operate with 64 different colors, then we need 64 independent laser diode. As the emission color depend on the current of the laser diode, it is very important to stabilize these current sources. And also, emission color depend on the temperature of laser diode. And it's also important to thermally stabilize this laser diode. So this brings an additional complexity of stabilization and also the power consumption. So an array of laser is not an optimum solution for increasing the number of color or the number of wavelength channels. One of the best and optimum solution is to use solid-on microcomb as a multi-wavelength source. This particular multi-wavelength source can be generated from a nonlinear microresonator. By coupling a single frequency laser diode inside this microresonator, due to some nonlinear frequency conversion, we see many new frequency components coming out of this microresonator. This multi-wavelength source provides some key advantages over the array of the laser, which are following. This multi-wavelength source can be generated from a single chip. Also, this multi-wavelength source provides more than 100 comb lines. And what I meant from the easy wavelength alignment is following. Just by aligning one of these comb channels, we can align all the other comb channels. Similarly, if we stabilize one of these comb channels, we can stabilize all other comb channels, as compared to the array of the laser where we need to stabilize each color. So this provides some additional benefit over the array of the laser. In this slide, I want to give an overview of optical frequency comb, mainly the generation of soliton microcombs. We start with the single frequency laser diode. We couple this laser diode inside this microresonator with the help of bus waveguide. This microresonator has a high quality factor, mean it has very low propagation losses, and it has Kerr nonlinearity at a certain threshold power, and by adjusting the laser properly, we see two new frequency components with the help of degenerate forward mixing. If we increase the power further and adjust the laser properly, we see additional frequency components that are generated with the help of non-degenerate forward mixing. If we increase the power further and adjust the laser properly, we see a comb-like structure coming out of this microresonator. As I mentioned in my previous slide, the spacing between these comb lines is constant. A typical comb structure is shown in this figure, where the spacing between two comb lines is constant. And this optical frequency comb can be considered as a frequency ruler. As we know that we use this normal ruler to measure the distance, this frequency comb can be considered as a frequency ruler to measure the unknown frequencies. So this particular tool has been used to understand the fundamental physics, and it has been also implemented in many technical applications. One of the very important frequency comb state that I want to mention here is dissipative Kerr soliton. If we can properly design the dispersion and nonlinearity of microresonator, we can excite this pulse-like structure that will maintain its shape inside the microresonator while propagating. In time domain, it corresponds to pulse of train, while in frequency domain, it corresponds to optical frequency comb with the envelope of secant hyperbolic square. One of the example of optical spectrum of soliton is shown here in this figure. The other key advantage of this particular state is following. This particular state is intrinsically low noise. So you can think about all these comb line as an individual coherent laser that can be used to transmit the data, or they can be used for the different relevant applications. Now I will discuss all the experimental work we have done in this project. The first part is soliton generation. So we started with a single frequency laser diode. Then we amplified this laser in order to overcome the coupling losses. So this package device has around 15% coupling loss, which is very low. If we provide enough optical power and adjust the laser properly, we can excite a single soliton. This soliton has an envelope of secant hyperbolic square. 3 dB bandwidth of this spectrum is around 40 nanometer. The FSR of the microresonator is 100 gigahertz. So we can use around 16 coherent carrier for the optical switching and communication experiment. We did the further amplification of the single soliton in order to meet the power requirement for the experiment. The post-amplified spectrum is shown here. We have achieved maximum power up to -4 dBm, and most of the channel has optical signal to noise ratio around 34 dBm, which is enough for the experiment that we want to carry on. After generating the single soliton, we picked only single comb channel. If you see this spectrum, we only picked a single color from this spectrum using this element AWG, and we sent this signal through SOA, which is an optical switching element, and then we detected this signal on the photodiode. So if you see the detected signal, we can clearly see that we were able to turn on and off this signal at sub-nanosecond timescale. We similarly tested more than 25 channel in C-band, and they showed the sub-nanosecond switching. In the following experiment, we have picked 4 different comb channels from the soliton spectrum. And then we use 4 different semiconductor optical amplifiers to switch these comb channels simultaneously. We applied a modified control signal in order to switch these comb channels. The signal detected on the photodiode shows that we can switch 4 comb channels simultaneously at sub-nanosecond timescale. The maximum optical separation between 4 comb channels that we have shown is 20 nanometer. Just to mention that we were limited by the optical bandpass filter, not by the soliton microcombs. In order to show a system level demo, a Mach-Zehnder modulator is used to encode the data in the form of NRZ and PAM4 on the simultaneously switch 4 soliton lines. If you see in this graph, a performance below forward error correction threshold limit for the data center is achieved for both NRZ and PAM4 data transmission at a different received optical power. This shows that Soliton Microcomb can be used as a potential multi-wavelength source for the future data center after certain improvement. All the experiment that I have shown till now has utilized these discrete SOAs, which are very attractive for the proof of concept experiment. But in order to demonstrate the switching and data transmission for the future and practical application, it is very important to demonstrate these applications at the chip scale level. So this chip was designed by the Microsoft Research Cambridge team. It contained 19 SOA and AWG. So this particular photonic chip provides the advantages of compactness and energy efficiency. So we performed the similar experiment that I have shown till now using the discrete component. First, we performed the switching experiment using chip-based SOA and AWG along with Soliton Microcomb. So we picked two comb channel and we showed that it is possible to demonstrate sub-nanosecond circuit switching using chip-based SOA and AWG. Similarly, we perform a data transmission with the modulation format of NRZ and achieve the performance below forward error correction threshold limit. Due to some technical issues, we were not able to demonstrate the PAM4 data transmission. We are looking into the possible reasons such as comb power, OSNR, and crosstalk between AWG channels in order to improve the performance of our system for the future experiment. The next thing that we also want to improve is the power efficiency of our devices. So we have identified several parameters that we want to improve. The first thing that, as I mentioned previously in one of the slides, that the total coupling efficiency of this packaged silicon nitride microresonator is 15%, which is very low. The main limitation is 2 dB splicing loss. So we want to reduce this splicing loss around 0.2 dB. This will improve our coupling efficiency around 30% and increase the power efficiency of our system by 2 times. The next thing that we want to improve is the dispersion of the microresonator. By engineering the waveguide width and height, we can engineer the shape of the spectrum that will be generated from that particular microresonator. This will eliminate the need of post-amplification, and the spectrum can be directly used to perform this optical circuit switching and the data transmission experiment. And by eliminating the need of post-amplification, we can improve the power efficiency of our device. It was recently demonstrated that Soliton Microcomb source can be generated from a on-chip laser without requiring frequency stabilized laser. This fully integrated Soliton Microcomb source can be interfaced with fully packaged SOA and AWG photonic chip. This will provide a path toward fully integrated on-chip sub-nanosecond optical circuit switching and data transmission. Before finishing my presentation, I would like to show the different application of Soliton Microcombs. In order to show that this Soliton Microcomb can be used in many different applications. The first application that I want to highlight is a coherent communication, in which a Soliton Microcomb can be used to transmit data at the rate of 55 terabit per second. Similarly, Soliton Microcomb can be used to perform the medical imaging. Very recently, our group has shown this thing that Soliton Microcomb can be used as a parallel source for frequency modulated LiDAR. And it can be also used as a calibration for the spectrometer to detect the exoplanet. So this shows that Soliton Microcombs cover a wide range of applications. Before concluding my presentation, I would like to acknowledge certain people. I would like to thank the Optics for the Cloud team at Microsoft, especially Sophie and Kai, who carried out most of the experiment that I have shown in today's presentation. Similarly, I would like to acknowledge my group at EPFL, especially Maxime, Zin, Anton, and Junkyu, and my professor Tobias Kippenberg. And thank you very much. If you have any question, please feel free to ask. Thanks again. Bye.
Thank you very much, Arslan, for the very nice talk. I believe Arslan is here with us to answer any question that we may have. Arslan?
Yeah. Can you hear me?
Yeah. Perfect. Yeah. So I think it was asked on the meeting chat about the reasoning not getting down for BR not to go below 10 to the minus 9, and Sophie answered due to the length of the data sequence, and Nicola Calabretta was still asking which sequence it was used.
And Sophie already answered.
Already answered. Yeah. Any other question for Arslan? Yeah, Tom Gerard has a question. What's the optical conversion efficiency for seed laser into the micro ring resonator?
So the conversion efficiency of, from pump to the adjacent comb line that are in 3 dB bandwidth in solitary microcomb is around 2%. So the net power existing so if you take out the pump, then I think we have around 4 milliwatt of power coming out of from this micro resonator. So the conversion efficiency is 2%, and the net power of comb that are basically coming out is around 4 milliwatt. And if you want to know the absolute power of each comb line, I think we have like around -20 dBm. So then we did the post amplification as I mentioned in my presentation. So the power for sure is not very high in the comb line. So one of the reason I also mentioned in the presentation, the coupling was very low. It was around 15%. So we were not getting too many, power in our comb line. Yeah.
Okay. Then. Georgios Servas has another question. He's asking, what is the definition used for switching time, rise or settling, and what was the overshoot that appears on the scope?
So the rise and fall time, I think it was like from 10% to, like a standard definition from 10% to 90% of your signal. Okay. And the overshoot that we saw on the chip-based experiment, I think there was a mismatch between the probe that we were using on this SOA for the chip-based SOA. So there was an impedance mismatch that led to this overshoot in the switching signal.
Yes, so then we have another question. Is there any specific reason for using silicon nitrate for the micro ring resonator?
So yeah, it has it has very low losses, as we know that the initiation power really depend on the Q factor. First thing, it has also relatively very high kernel linearity, which is required for generating these microcombs. And also, we can fabricate this thing at the chip scale level. So these are like a three normal, like a top level reason I can tell you here why we use the silicon nitride. Yeah.
Perfect. Then just to be on time, I don't see any further question on the chat, but feel free to approach Arslan by email if you have any further question. I will then like to move on to the next speaker, who is Wenjing Tian. Wenjing is a member of the Photonics Integrated Group at TU Eindhoven, under the supervision of Professor Javier Legentens. Kaishi is a professor, he's a Microsoft supervisor. She's working on hybrid integration photonic circuit system based on indium phosphide and silicon nitride, and their corresponding integration, which is one of the greatest barriers to deploy optical switching technologies. And today's her talk is about cost-effective assembly for hybrid integrated photonic switches. And let's start her pre-recorded talk, which will then be followed by live Q&A, where Wenjing will be able to answer. Thank you.
Hello everyone, this is Wenjing Tian. Thanks for joining my presentation. Today I will talk about cost-effective assembly for hybrid integrated photonic switches. Let me show the content of this talk. First, I will briefly introduce the field of photonic integration and give you a sketching of our project. Then I will spend most of my time on our proposed assembly concept and 3 designs of photonic integrated circuits as demonstrators in this assembly route, say a photonic switch, a multiplexer, and transmitter. There are three key elements in data centers, range from optical source over WDM to optical networking. Of course, since time is limited, I will not go into detail about each design. I will mainly focus on the photonic switch. Finally, I will give a short summary. Let's start with photonic integration. What comes to your mind when you think of it? Basically, photonic integration is a technology of combining many optical device components in a single circuit, interconnected by waveguides. We call it Photonic Integrated Circuit, or PIC. It's enabling lots of applications, for instance, telecommunications, healthcare, and data center networks. This widening range of applications can be implemented by one generic integration technology. Here are some examples of PICs based on indium phosphide platform. As you may know, indium phosphide is a direct bandgap material and could generate light. It can enable various integrated lasers, such as OCD lasers, WDM transceivers, and LiDAR. It can also benefit biosensing and recent quantum key distribution. With this kinds of PICs, we can achieve great performance, such as reduced footprint, improved stability, and reduced energy consumption. It's also good to know all the PICs presented here are roughly 5 millimeters long. Naturally, these benefits can be extended to data centers. Microsoft is actually using the same platform to investigate data center applications, for example, fast optical switching. Imagine a data center. There are hundreds of thousands of servers and optical transceivers. In such a complex optical transmission system, optical interconnects between fiber and photonic circuits are happening very frequently. So efficient fiber-to-chip coupling is crucial. However, we are facing a huge size mismatch between a fiber core and an optical waveguide on chip. It can cause considerable transmission loss and limit the scaling up of capacity density. To date, various methods have been proposed. For example, using an interposer between fiber array and photonic die to fan in, or using a fiber stop to match with waveguide array with polymer buffer integrated on chip. Roughly speaking, current solutions can either support many connections, but in a tight alignment tolerance, or it can give a relaxed tolerance, but limited connections. Another concern is photonic assembly and packaging. The gold box packaging makes it even more difficult for a large-scale fiber array coupling. Not to mention the gold box packaging is quite expensive. All these challenges drive our work to find a solution that can enable many connections with relaxed tolerance in a cost-effective way. Now, let me introduce what we are doing. We are investigating an assembly method for hybrid PICs, especially for photonic switches, by leveraging two technologies, indium phosphide and triplex technology. Few more words about triplex. It's based on alternating silicon nitride and silicon dioxide films. To take our assembly method a bit further, as the picture shows, a triplex die is utilized as a kind of photonic PCB, on which indium phosphide bare die will be flip-chip bonded. Particularly, flexible and free-hanging waveguide on triplex are connected with a fiber array and will be aligned onto indium phosphide. You may be interested in the flexible waveguides on triplex. We will see how it works. Let's move to the assembly concept. As for the flexible waveguides, they are implemented by silicon nitride-based triplex technology. We call them fingers. Each finger has a waveguide inside, as shown in the schematic view. TOE has developed this method to enable optical interfacing. you can regard the fingers as spot size converters between a fiber array and chip. You can weakly say this is a finger array, one side connected with a fiber array, and the end of the fingers will be aligned to a chip. This approach can support up to 40 connections per millimeter, as shown in the picture here. This is an example of 64 fingers with a pitch of only 25 microns. You may ask, how can the fingers bridge a fiber array and chip? We will say it later. In this slide, you can clearly see how the triplex fingers are aligned to the funnel-shaped landing zones on indium phosphide, especially in these two pictures, picture C and picture D. This is the alignment procedure of an array of 4 fingers. In the upper one, before alignment, the 4 fingers are moved to somewhere above the chip, and in the lower one, they are landed in the funnels on indium phosphide and then aligned to the waveguides. Here's another example of more than 30 fingers alignment. In the higher level, when the indium phosphide die is being filter bonded, triplex fingers can be passively aligned into the dedicated funnels on indium phosphide without optical signal monitoring. So this is the general idea of our assembly concept. We are looking for applications using this assembly concept that are both good for data centers, also requires many optical ports. Hence, a wavelength selective and space photonic switch, say WSS, might be a good option. Next, we will see the design of the PICs. It's good to mention that we are using standardized layouts of indium phosphide and triplex tubes throughout the project. Here are the mask layouts of 2 tubes. The main optical function will be provided by indium phosphide, and the triplex is utilized as a carrier on which the indium phosphide will be filter bonded. All the 2 tubes have specific dimensions and locations of electrical paths and, of course, optical interfaces, say the fingers and the funnels. All these specifications can be transferred to functional designs. As I said, for example, WSS, aiming to show the proof of concept. Now it's time to see the WSS. It's a 4x4 WSS cross-connect. This is the schematic view. It has 4 inputs that fan out to a shuffle network, followed by 16 gates for broadband input selection, and 4 wavelength demultiplexer with another 16 gate for wavelength selection. Then a final fan-in connects to 4 outputs. This WSS is based on the previous work done at UE. However, it will be the first time to try in our proposed assembly concept. So we redesigned the WSS using the standard layout mentioned previously. As you can see, there are 16 optical connections on each side of the chip in a 4 mm range when using 50 micron pitch. It could be doubled if we use 25 micron pitch. As for the WSS, it has 8 inputs and output ports. As you can see, light is injected into 4 parallel waveguides and then fan out to a shuffle network based on crossings and cascaded 1x2 splitters. 16 semiconductor optical amplifiers, say SOA, are here as gates to perform broadband input selection. As for the SOA-based gates, they are electrically controlled. In the on state, the signals are amplified, and in the off state, they are strongly attenuated. Then the amplified signals are transmitted to the wavelength selection stages. Each stage consists of a 4x4 cyclic array waveguide grating router, say AWG, and 4 SOA gates at the output ports of AWG to perform wavelength selection. Finally, cascaded 2x1 combiners are here that fan in the light connects to the output ports. It may be good to say more about the SOA-based photonic switches. The SOAs can not only provide faster switching in nanosecond precision, but also optical amplifications to compensate for on-chip losses. Besides, I would also like to give you a favor of other two designs. The first one is a 40-channel modulator array, multiplexed by an AWG onto one single output. This is also what the schematic view shows, using 40 off-chip lasers. The reason why we use off-chip lasers is the electrical absorption modulator needs a bandgap offset for detuning, so we can't use integrated lasers. Also, the two photodetectors and other outputs are there because of parameterization and reductancy. The second one is a transmitter chip with two widely tunable lasers. Microsoft is interested in this widely tunable laser for product series. The chip is designed to try the idea of nanoscale wavelength switching, tune the right wavelengths while the other laser is transmitting. As I said, I can't go into detail about all the designs since the time is limited. If you are interested, please raise questions after the presentation. The three designs of indium phosphide PICs have already been submitted to a multi-project wafer run on a mature foundry platform of smart photonics. Also, the triplex chips and fingers are being fabricated by Lionics International. After the fabrication process is done, the two chips will be combined and an assembly tool from Ficantech. We are collaborating with these partners in a joint European project, Eurostar project. We are targeting to try the flip chip assembly concept in different levels, in a die level, to a bar level, and finally a wafer level. Then a system demonstration will be put forward in the lab of Microsoft Research Cambridge. All right, let me close my talk with a brief summary. Well, what I have tried to say today is a new assembly method for hybrid PICs by leveraging indium phosphide technology and silicon nitride-based triplex technology, especially using the finger-based flip-chip bonding assembly for the hybrid PICs. We are exploiting this method for emerging data center applications that need high-density fiber-to-chip coupling. As I said, our objective is to demonstrate a cost-effective assembly method that could enable many connections in a relaxed alignment tolerance. 3 demonstrators ongoing range from light generation to light manipulation, especially optical switching. I'm excited to see what will happen soon. Finger crossed. So this is all I have for today. Thanks for your attention.
Thank you very much, Wenjing. I believe she is now online.
Yeah.
Yes, excellent. Yes. So I can already see a couple of questions in the chat. So let's start from the question from Ben Thompson. He's asking if the flip chip bonding of the indium phosphide die to the triplet carrier means that you no longer have to bring all the electrical connection to the edge of the indium phosphide chip. And then can you instead do this electrical routing on the triplex chip?
Okay. Thanks for the question. As you can see, Xavier has already replied it. It says in our demonstrations, we have the predefined paths, the electric paths on the each side, the north and west side, north and south side of the tube. So we do need to route the metal tracks to the predefined path on indium phosphide, and then through the full object bonding, the electrical pies on indium phosphide will be, as I bonded onto the triplex tube, and then we will drive the indium phosphide tube by the metal connections through the triplex. Yeah, I hope this answers your question.
Yeah, no, thanks for that. I mean, the reason I ask is sort of having designed some of these chips before is you sort of spend an awful lot of your precious optical chip area used up for routing electrical connections. This seems like a really nice way of getting around that problem and sort of heading towards, in electronics we've had multi-layer chips for many years, whereas in optics we're still sort of an optical layer and a single electrical layer. And I think this looks like a really, really nice way of getting around some of those challenges. So yeah, no, thanks for that really nice presentation.
Okay, thank you.
Excellent. So we have another question from Xian Li. He is asked, what is the coupling efficiency, and what is the signal stability? Since I saw it looks like suspended, and can it be used for SOI?
Okay, all right. Thanks for your questions. Regards for the first question, as you can see, I just demoed the mask layout of 3 designs. So we couldn't have the fabricated chip in-house, so we haven't do the coupling efficiency now. So I can't give you an exact number for this question. I'm sorry for this. And for the second one, was it the signal stability? I don't know if I understand your question correctly. Maybe you can explain more about this. I'm sorry for that. I don't know why you asked this question.
Yeah, sorry. Probably I didn't understand very well as well. So I'm wondering, because this is transfer optical signal from the fiber to the chip, if I'm correct.
Sorry, transfer what? Amplifier or?
No, optical signal, like.
I think the main question is, sorry.
I can step in if that helps. I think these fingers, they're like spring loaded, so they will stay in place because of the mechanical force that is holding them there, and then they will not move even if there's temperature changes or a temperature mismatch in the expansion of the different chips. So the spring loading keeps them in place, so that makes the signal stable. Is that answering the question?
Yeah, thank you.
Okay, thank you. Yeah. Okay, so regards for the third question, I think in principle the approach can be extended to silicon photonics chips. It's only required that we adapt our design of the finger and the pitch, and of course the funnels on silicon chip rather than the indium phosphide chip. I think in principle we can, but we haven't tried this now. Yeah.
Perfect. Thanks. And we also have the last question from Nikolaos Bamiedakis. He's asking if you have some values either from simulation or experiments for insertion loss, so coupling loss and alignment tolerance for your scheme.
Okay, thanks for the question. And I think we do have some experiments results for the alignment tolerance, because we utilize the finger connection, not for this full object bonding, but for a kind of on-chip probes to connect with the indium phosphide waveguides. And based on the previous result, the alignment tolerance can be as ±2 microns, which gives a relaxed tolerance for the fingertip It's about 50 nanometers. I think this is what we have in previous experimental results, but we haven't done in the Philip bonding concept now. So I think we will give more results and data in maybe for the conference, I hope. Yeah, thank you for the question.
Excellent. I don't see any other. Yeah, okay. So I don't. Oh, I see a raised hand. Is Fotini, please?
Yes, just a quick question. I was wondering what is the maximum number of fingers and what is actually the limitation for this technology to increase the number of fingers? If you could comment a bit on that.
Okay, thanks for your question. As you can see now, we are using the 15 micron pitch for the fingers. And as I show in the design, there are totally 64 fingers on each side of the chip. You can easily decrease the pitch to 25 micron, which promises 40 connections per millimeter. It means we can have 128 fingers on each side. And you can even reduce the pitch a little bit more. I mean, to, for example, 20 micron pitch, it can give you more connections. But I'm afraid we couldn't do more because the finger width is 10 micron. We still need some space in between two fingers. So I think the maximum scalability is around 300 to 400 per in a whole chip in two sides. Yeah, I think.
Thank you.
Yeah. Okay.
Thanks a lot. Very good talk. Thank you.
Thank you.
Thank you very much, Wenjing. I don't see any other questions on the chat. So I would like to thank you once more and move on to the third speaker. So the next speaker is Jingtao Hong. Jingtao is a member of the photonics group at the University of Cambridge under the supervision of Professor Daping Chu. Andreas Georgios is his Microsoft supervisor. His work relates to pixelated spatial light modulator for phase and polarization modulation of light. And today his talk is about phase and polarization spatial light modulator systems for optical data storage in glass. Jingtao will present live and obviously will be here for the follow-up question and answers. And if Jingtao, you wouldn't mind to, so Scarlett will progress your slides. So whenever needed, if you say next slide, please, Scarlett will be able to progress on for your presentation.
Okay.
Thank you. And the floor is yours, Jingtao. Thank you.
Yeah. So, can everyone see my slides?
Yes, we can.
Okay. So, good afternoon, everyone. My topic is phase and polarization spatial light modulator for fast data writing on optical data storage. First, I would like to introduce the application, the purpose of this project, writing data on glass. By 2020, more than 39,000 EB data will be generated by human. So here comes the question. That colossal amount of data, how can we store them? So there's normally 5 criteria to evaluate a data storage technology, which are first, storage density, second, stability and robustness, third, power consumption, 4, record and access speed, 5th, the last one, of course, is cost. So after thinking about this 5 criteria for data storage technology, if we store the data on the using glasses, we can have the following 3 amazing advantage. First is ultra high storage density. because the data optical storage using glass can provide you 5 dimensions of data storage density. And also, because we're using glass, so they will give us a very low cost in making the storage medium. And also, because of the high thermal and chemical stability of glass, which means we can use this type of data storage technology to store cold data. So that's why there's a lot of brilliant scientists start a project called Project Silica to realize the optical storage system using glass. In the beginning, I want to briefly introduce the Project Silica, writing and reading data using glass. So writing data, we use a femtosecond laser, which can create multiple pulses in a very small area of in the glasses. This can create a nanostructure which has orientation and amplitude. That 2 parameters is how later we define as the bits where the information was stored. And this part, on the writing part, is my work is focused on. On the reading side, on the data reading side, the data is reading use a polarizing microscope, which can give you the birefringence and the retardance information on the small nanostructure. And this is the Project Silica. Next. Because this work is focused on the data writing, so the target bandwidth is something we really care about in data writing. Here I use example to explain what is target bandwidth. For example, if we assume the data writing speed is 400 millibits per second, is similar to a current Blu-ray writer, and we also assume 4 bits, 1 symbol, and the symbol means the 1 nanostructure or voxels in the glass, and this can give us a target. Is we have to store 100 million symbol in 1 second. In another way, in another word, is 1 symbol every 10 nanoseconds. That's a very, very short time. So what about how can we write the voxels in the glass? Currently, we have 3 ways: sequential, parallel, and mixture of both. And this work focus on the parallel writing. So next, I will explain the idea and the mechanism of parallel data writing. Followed with the example I made. If we do the full sequential writing, which means every symbol we have to finish within 10 nanoseconds. That's a very short time. However, if we choose parallel writing, we can writing more than 1 symbol at the same time, which means if we follow the time writing speed, the parallel writing become more deep, we can see we can have less requirement on the writing speed. And now, because of the writing, we use a specialized modulator, which means the current one we can use DMD or LCOS, which means if we can make parallel writing possible, we can have better or more choice on the choosing correct specialized modulator. So if we combine multiple LCOS devices and other scanning technique, we can increase the writing speed and also have more choice. Now I want to add a slide to talk about the comparison between the parallel and the sequential data writing. If we write data sequentially, means 1 symbol at a time, and every symbol, every voxels actually requires more than 1 pulses, normally around 400 pulses. So yeah, that's the time we need. And also because we write symbol sequentially, means we have to continue, always need to move the glasses to the correct position to write the symbol. And because of the frequent moving of the glass will lead to the very large mechanical delay. So this will give us lower writing bandwidth. This is how we define the writing bandwidth. However, if we're writing parallelly, means many symbols at a time, this directly leads to less glass movement or slower movement. This will dramatically reduce the mechanical delay in the writing, which means we can get a much higher writing bandwidth. And this is something we want on the data writing side. So next thing I want to next step, combine SLM and parallel writing. Because the beam rate, the writing beam, if we think about fundamentally, it's just multiple beams, and each beams with the wanted or desirable state of polarization. As for the multiple beams, L cos SLM can create multiple beams with very low energy loss, and each beam can have a desired intensity. That's why L cos SLM is a very powerful tool for generating multiple beams. At the same time, L cos SLM can also provide polarization modulation on each beam. So L cos SLM can be a very useful weapon. There are now normally two approaches to generate the writing beam. The first one is combining SLM and also a polarization modulator. And the second approach is using two SLM with a orthogonal polarization. And each SLM I encoded different information and data on the vertical and horizontal light component. And the two SLM system is my work my work focused on. Okay, now I want to explain the two way I just mentioned, two approach to writing data. First one is combine a single SLM and the external modulator. The laser give the incident beam to the SLM. The SLM actually split the beams, and the beams pass the polarization modulator to give them wanted polarization state. So we can see on the right of the page that on each time the writing system writing one kind of beats. For example, 00 or 01. I use different color to show the different beats. So we can see there's a problem very clear. If we use this way to generate the writing beam and do the data writing, so the power loss will be a lot. For example, on the first writing, we only have one dot with 10, means there's a waste of all other energy. And also, if we have a lot of 00 here, means there will be too many dots we have to write at the same time. That will cause some power problem on the writing. So this is what the problem we'll have if we use the SLM and the external modulator. However, if SLM can do both beam splitting and the polarization control, what we can have here is, and the writing procedure will be, on each time, we always write the same number of dots, which means this can get rid of the problem that the distribution of energy. There won't be too less dots with bigger with a lot of energy, or too many dots with each one with a inadequate energy. This thing, and also in this way we can maxing the power oscillation as mentioned, and also the writing bandwidth, as we see in the page that after the first writing we write a 4 out of 8, and the second time we write of another 4. So only 2 circles can finish, and the previous method we need 4 circles. So it's already an increase of the writing. So next part, I will share with you guys about my experimental work. There will be 3 parts. First is how can I make using SLM as LCOS to realize the polarization and phase modulation at the same time. And the second one is how can I get rid of the zero order during the diffraction. And last part is how can I do a further improvement in writing is aberration correction. Now let's go to the first one. Okay, now I will give you guys a brief introduction about how we use the alkos SLM to work. On the left is a schematic of a crystal molecule. We can see the shape like this, and on the longitude and on two sides, it has different refract index, which give out birefringence. By introducing the electric field on the alkos, we can actually move in the liquid crystal molecule, which means we can change the effective refract index that the passing light experienced. And this can give us phase modulation. And the phase modulation means we can use it to realize beam splitting and information encoding. Yeah. And in this work, all the SLM I use is reflective mode. And the schematic of the reflective mode alkos is here. So we see the transparent electrode and the liquid crystal layer, and behind it is driving board is the back plane. So this is the optical schematic, and the real setup I use for the is the phase and polarization modulation system. So after the light passing from linear polarizer, there's a 45-degree, and the orange one equal the vertical one, and blue one means the horizontal one. So after passing the first SLM, I can encode data pattern on the orange part. After that, I put a halfway plane here, so it rotates the polarization state of the light, which means now the light state will be like this, and then the light passing on pass to the second SLM, which have another data pattern, and the blue light component will have a different data information, which means now we can see the horizontal and the vertical light component has already been encoded on the data. So yeah, this part is a video I shoot in my experiment. Let me play. So this part is I didn't put anything on the polarizer at the outcome. So it's outcome with light field without polarizer. And now I will put on a polarizer. Now the polarizer on, and then I start to rotating the polarizer. Now we can see two dot beam, which is 4 times 4 and 5 times 5, and I keep rotating it. One light component disappear, and keep rotating. The 5 times 5 disappear. Now this show one thing. I successfully encoded two different diffraction pattern or data pattern on vertical and horizontal polarization state of light. And this means, yeah, polarization state control and also beam splitting. So we can see this another shot from the video. So the replay field after polarizer is the both 5 times and 4 times 4 together. When I put the vertical polarizer here, we can only see the horizontal one. And also, if we put the horizontal one, the rest. When I put the plus 45-degree polarizer, we can see the reduced the amplitude of both pattern. Yeah. So that's the system, which is on the big optical table. Now next time I will work on the compact system. Means I will make the big system into a size of like our hands. So I will make a compact system. The two SLAM will be replaced by one, and the whole optical path and system will remain the same, but everything will be very small and one SLAM. I will separate the SLAM into two area to do what I just did using a big optical table. This can bring us very low spatial shift between the two sequencing modulation, and also higher alignment precision, and also the system is compact. It will be more feasible for the real application, practical application. Okay, another part. Let's move on to the second part, zero order reduction. So yeah, when we use SLAM, diffraction, we'll have a zero order, which is the unmodulated beam. If without the zero order defocusing, we will have a very strong zero order beam and also our wanted information or data here on the same focal plane. This will lead us a very big problem is zero order beam have a very high energy, and this can damage our glass. Is something we really don't want. So I study the way to how to defocus the zero order, or I just shifted the focal plane of our information and the zero order focal plane separately. The way is I encoded a Fresnel zone lens on the SLAM, which means we can see from the schematic. The black color ray is the zero order, and the dashed line, the blue one, is our information. So because the zero order is unmodulated, so I encoded the lens on the SLAM will not affect the zero order, but it will only affect our diffraction beam, which is first order. So we can shift their focal plane separately. And this is on the left is the glass data hologram, and also I add a zero order defocus lens. And this is the experimental result. On the far, we see the first picture, the first photo I took is the zero order beam focal plane. We can see the error order is focused, and the rest of the data is defocused. This is from the plan here. And on the plan B is our information plan. Yeah, we got our information focus, but zero order, the energy is defocused. Also, this picture is, I want to show this zero order beam. The energy of zero order beam on our information plan has already below our writing power. Yeah, so it will no longer affect our data writing process. And also you can do something like blocking the zero order. So on the picture on the right, you can completely remove the zero order even on your focal plane by blocking it. The last part is I want to go more quickly. Is about aberration correction. Is very straightforward idea, because we need to focus a light from the air to a glass, which means there will be a very high refractive index mismatch. And also the lens we use to writing normally have a very high numerical aperture because we need higher energy and less. If we move to another layer, don't affect the previous layer we already write energy on data on. So, however, the high numerical aperture lens will make the focus distorted, which means we have on our desired focal point, we have a lower focal intensity, and also because the lower storage density, because each layer of data we need more distance. So I want to pre-operated our waveform by using SLAM to get a non-distorted focal point, which give us high focal intensity and high storage density. How to do this is we need to find a correction phase. We have to first if this is the focal without any refracting index mismatch, we have a geometric focal point. When we add on the refracting index mismatch, The right beam is the beam we focus from N1 to N2 medium and focus at the same point. So this one we can calculate the phase operation phase here. However, this will give us very high magnitude of the phase if you want to focus them in the same point. So we will cut out the defocus phase. We will set our desired focal point lower than the geometric focal point of the lens, which give us less required phase modulation magnitude. So we can use this way to calculate what the correction phase we need to actually give us a perfect focal point on the level of B. So we can see from these two simulation results that on the first one, on the left one is without remove the defocus phase part, we have a phase range required like over 40 pi. After that, we can decrease almost to the like 10 pi. However, it's a huge decrease in the needed phase modulation magnitude. But as for the Alcosel SLM, we only have 2 pi phase modulation range, which means we have to find a optimum defocus factor, which means is the distance between our nominal focus point and our design focal depth to get the required phase modulation range within the 2 pi. That's how I found it using the math equation. If you're interested, you can ask me later. So this on the right is the phase profile we can put on the SLM, which give us the good focal point in the glass. So that's all of my talk. So I did the phase and polarization modulation system for the writing beam, and also I get rid of the zero order because I'm using SLM. That's something I get. And also I'm thinking about removing the aberration in the focusing point in the glass, also using Alcosel SLM. Okay, thank you everyone. Thank you.
Thank you very much, Jintao. Are there any questions? Yeah, I see a couple of questions. The first is from James Fleck. He's asking what type and model of spatial light modulator are you using, and what is the bandwidth of the spatial light modulator in terms of pixel per update frequency?
Thank you very much. Thank you, James. The type of SLAM I use is pneumatic and pneumatic SLAM, which give us 256 gray level. And also it's a reflective mode. And the bandwidth, I think you mean probably the frame rate. So the current one I use just a normal one with the, I think it's 60 Hertz. It's just a typical pneumatic SLAM frame rate. And yeah, thank you.
Fantastic.
Okay.
Thank you.
Yeah, thanks.
If you we can go through quickly the last question from Masaki Sakakura. He has several questions. He's asking, how about the phase stability between the two spatial light modulator? And he's also wondering if a small temperature change could induce the instability of the polarization.
Thank you very much, Masako's question. So, how about the phase stability between two SLAM? I think how I understand your question is you mentioned the phase flicker because during the modulation you have a flicker in the phase modulation, and if you say during the modulation, why I make a compact system is because when we want to have the diffraction pattern, first order diffraction, we put a confocal lens, which means we just make everything in the far field. However, in practical, there's a distance between there's a distance between two SLM, like you say. So what I want to do is I want to decrease as much as I can the distance of the two SLM, the two modulation, which means this can give us almost far field replay field for our diffraction. So I think that will somehow making the phase shift during the propagation of the light smaller. And I think temperature will also induce the instability of phase modulation, because now the device is the phase only LCOS. So yes, there will be, but the something affect the phase the polarization modulation more is the retardance, is the and flatness of the LCOS cell. So I think that will affect more than the temperature now.
Fantastic. Thank you very much, Jintao. I see that Masaki has another question. Andreas replied, but if he hasn't, if I would like to ask you, Jintao, to reply through the meeting chat so that we can move on to the next speaker. Thank you very much again, Jintao.
Thank you very much.
So the next speaker is Hubert Dziecioł. Sorry, hopefully I pronounce it okay. Hubert is a member of the Optical Networks group at UCL under the supervision of Dr. Dominic Lavery and Professor Robert Killy. Christos and Fotini are his Microsoft supervisors. His works relate to transceiver subsystem for inter and intra data center optical fiber communications. And today his talk is about phase noise tolerance in ultra-dense wavelength division multiplexing access networks. So let's start his pre-recorded talk, and this will be followed by question and answer where Hubert will be able to answer questions.
Hi everyone. In this talk, I would like to show you an idea of how to implement low-quality integrated lasers into ultra-densely multiplexed coherent access networks. To make it clear, the main goal of this work is to connect a large number of users of the residential areas to the internet by multiplexing a large number of channels in the same line, which, as far as I know, is not something that you would normally do in a data center. However, the techniques presented in this talk can apply to any short-reach coherent optical fiber communication system that you would like to have. I'd like to start with introducing you to a little known but accurate metric to predict the future bandwidth requirements of the access networks. It was invented by someone called Jakob Nielsen, who works as a technology consultant and has been plotting the maximum available connection speeds to his house for the past 38 years. And apparently, it turned out to be a weirdly accurate prediction called Nielsen's law. It is shown as the red curve on the right-hand side, and as you can see, if we look at 2019, where he could get 325 megabits per second to his house, it's not that far from the red curve, which is the prediction. So if we extend that curve until 2024, we can see that the expected throughput requirements will be around 10 gigabits per second. At the same time, we would like to have these throughputs both bandwidth and cost efficient. For the same reason, many researchers are starting to look into simplified coherence schemes, as they offer better receiver sensitivity, you can use advanced modulation formats, and they are also wavelength selective because you can tune the local oscillator laser to many wavelengths. The idea of coherent, ultra-dense WDM access networks was originally proposed as 1 terabit system with 1,000 channels of 1 gigabit per second by someone called Rode. It offers great network flexibility and bandwidth utilization. And 5 years later, in 2014, Samuel called Rice has experimentally demonstrated that it can work over the bandwidth of 12.8 nanometer for 192 channels of 10 gigabits per second. However, there are specific challenges when it comes to this system. First of all, because we have a large number of channels, we have to operate at low symbol rates between 1 to 2.5 gigabaud. So automatically, many of you will assume that we need low line width lasers, otherwise there will be too much phase noise. So let's say if our lasers has to be 100 kilohertz or less, and also tunable, from the practical point of view, this is a lot of money, and that money will probably not come back. So another thing that we have, which is not everything here, is the power budget requirements, which has to be low because we have to keep this network cost low. It's just a residential area. So the main motivation for this work was the fact that there is a lot of low-cost integrated tunable lasers available on the market. However, they're all quite noisy, which means they have line widths of 1 megahertz and above. But we know that we can enhance our phase noise estimator by adding some sort of hard decision regions for the residual phase noise. And we also know from our previous work at UCL that you can improve the power budgets of the coherent 50 and 100G access network by doing the constellation shaping. So to summarize the problem here, our system has tons of lasers that we want to multiplex as a large number of channels in the same pipe. However, these lasers are assumed to be very expensive, so we want to get rid of them and replace them with like relatively cheap, low-cost integrated lasers and deal with the phase noise that comes as a result of it. So therefore, we have to look into DSP and extend the phase noise tolerance of our ultra-dense WDM access networks to make it more practical for the implementation in real life. To deal with it, we adopted a system model, such as in the original experiment in 2014, which transmits 32 symbols over 2 states of polarization at the symbol rate of 2.5 gigabaud. So we aim for the effective post-fake data rate of 10.325 gigabit per second per polarization, which is the same as 10G Ethernet traffic. If you look at the right-hand side, we have this equation here, where X are the originally transmitted symbols, Y are the symbols received at the receiver, and we have 2 noise components. First of all, the zero mean AWGN, but we also have phi n, which is the noise of laser phase, which has a disturbance formulated as the multiplication of 2 pi, delta mu, which is the sum of the signal and the LO laser line width, and delta TS, which is the symbol duration. So first of all, before we jump into any phase noise mitigation strategies, we know already that the constellation shaping can give us significant power budget improvements. So we took 32 QAM gray mapped constellation and assumed that we are dealing with the EPON low density parity check code at the rate of 0.825 and shaped our 32 QAM constellation to maximize the generalized mutual information, which means that we are using binary sub-decision coding scheme. And this is the result of the shaping. Then we took 2 of these constellations and analyzed 3 different strategies of the carrier phase estimation. So the first strategy is also called pilot-based carrier phase estimation, where we insert QPSK pilots at the rate of 1/32, which formulates 3.2% overhead. Then, at the receiving side, we take those QPSK symbols and we put them through the Wiener filter and interpolate over the entire data frame. So as a result, we have these received symbols, the orange plot, and this is what we get at the receiving end. So if we follow with this system, we can see that for both 32 QAM, which is the blue dotted line, and 32 GS, which is the green line, you can see that at 1.5 megahertz laser line width of both the signal and the LO, the system breaks down. We are basically unable to reach the GMI threshold. If we look at 1 megahertz line width, we incur a massive SNR penalty of around 6 to 7 dB when it comes to comparing it with no phase noise scenario, which puts us in the power budget that is unacceptable in terms of the access networks. So this doesn't really work in practice. In the second scenario, we analyzed something that people normally do, which is adding this pilot CPE and then extending it with something called residual phase noise estimator, which is nothing else but the second stage, which puts the hard decision regions on our received symbols and classify them depending on which region they fall in. So in the second scenario, you can clearly see that the dashed lines representing our two-stage phase estimator have much better performance than the first one. However, with 1.5 megahertz lasers, we still incur a massive SNR penalty of 6 dB, and this is still not really good for practice. For 1 megahertz, well, we've gained 1.6 dBm, which is quite good, but we can still do better. Why? Because we are clearly using a suboptimal decision region. So if you look at these two pictures in the middle, the green and blue one, you can see that those decision regions assume that our noise is circular, but this is not the case, and our Euclidean distance receiver is not that good when we are dealing with that much of the phase noise, because phase noise is angular, and these decision regions in practice, they look quite differently. So in our third scenario, which is also the main contribution of this paper, we decided not to use the Euclidean distance decision regions for our RPE, but enhance them with a model that was proposed by our colleague Marty, which is aware of both phase noise and AWGN. It is a little bit more complex to compute, but now if we look at those decision regions, we can clearly see that they are aware of the phase noise of the lasers. As a result, you can see that those hard decision regions, denoted by the solid lines, are giving us better performance. And now, if we look at 1 megahertz system with 32 QAM and Euclidean distance hard decisions, and compare it with geometrically shaped 1.5 megahertz laser, we only have 0.3 dBm penalty between these two models, which means by doing this little trick, we relax the laser line width by almost 50%. To summarize this work, we get almost 50% relaxation on the laser line width when compared with 1 megahertz system. We also potentially reduce the cost of this system because now we can use it more noisy lasers. And it comes with a relatively low complexity trade-off because those hard decision regions compared to computing soft decision per symbol is the thing that we can pre-compute and apply on the chip. So the next stages of this work would be the practical implementation of this UDWDM access network system in the lab as soon as it goes online, and also looking into phase noise-aware signal shaping techniques to further improve these results. Lastly, I would like to thank my co-authors, Eric Silikens and Domanic Lavery, and also my supervisors, Fotini and Christos, for their great contributions. Thank you very much for listening, and if you have any questions, I'm happy to answer.
Thank you very much, Uber, for your very nice talk. Now the talk is open for questions. At the moment, I don't see any, so maybe Uber, if it's okay, I can kick off with a question. So if I understand correctly, you start with a very noisy signal, lasers at the transmitter side. Is that correct?
Yes.
Yes. Is it the same? So at the receiver side for the local oscillator, you still have, if you want, noisy lasers as a local oscillator, or in that case you require local oscillator with a narrow line width?
So the assumption here is that the line width you have on those result plots, it is a combined line width. But I would say I would assume that both of the lasers are the same, the LO and transmitter.
Okay, so that you can allow a very noisy local oscillator.
Yes, because this is for the combined line width. So
yeah.
We have 1.5 megahertz for both of the lasers.
Fantastic, thank you. Any more questions for Huber? Then maybe I have also another question. So basically, if again I understood correctly, you move the complexity from your laser source to the DSP that you need to use. Is this correct?
Yes. So the idea here was to take a cheaper laser and make the DSP more robust against the phase noise.
Yeah, but overall, there are more advantages rather than disadvantages to make your DSP more complicated, right?
I mean, like the idea here of this coherent ultra-dense WDM access network, it's because we have a lot of users on one end, we will have to have a laser per each user. Mm-hmm. So if we use these very low line width tunable lasers, they will cost a lot of money. So in general, we just wanted to take something that is much cheaper and prove that by doing something low in complexity in terms of DSP, we can make it work.
Yeah, perfect. Thank you. Thanks. Yeah. Any further question from the audience? I don't see any other. Yeah, Mark Harrington has a question, please.
Yeah, just real quick. So do you think there would be any implementation penalties as far as the hardware you need to run this slightly more complicated DSP, like in terms of maybe the ADC hardware or I guess obviously there would be some type of increased complexity in your DSP hardware, but do you have any ideas on if, like, for example, you might need a higher bit depth in your ADCs or something to that effect?
Well, I'm not sure about that.
I'm just wondering what types of how the increased DSP complexity would actually affect your implementation cost, if you have any ideas, but obviously no.
Not really. I think the easiest way would be to try it in practice, and maybe something will come out at that stage.
Okay.
But I don't know. Maybe someone can answer.
Yeah. All right. Thank you.
Oh, thank you very much, Mark. I don't see any further questions, so thank you. Yeah, I don't see any further questions, so thank you very much, Hubert, for your very nice and very interesting talk. So I would like then to move on to the next talk. But Hubert, if you see some questions that refer to your talk, I would like on the meeting chat, I would really encourage you to answer remotely, if you don't mind. Thank you. So,
okay, thank you very much.
Thank you very much. Thanks. So let's move on to the last talk of the session today. This talk will be given by Paolo Costa from Microsoft, where he will be primarily updating us on the exciting research that is carried out at Microsoft on the optical networking side. Paolo Costa is a principal research manager in the Cloud Infrastructure Group, and I believe now he will take the lead. Yeah, I can see Paolo. So he will present live. So is over to you. The floor is yours. Thank you, Paolo.
Thanks. Cool. Can you see my slides and can you hear me okay?
Yes, very well.
Okay, fantastic. All right, so hi to everyone. So my name is Paolo. And yeah, so Francesca was saying what we would like to do is just to give you a high-level overview of some of the challenges that we had to solve as we embarked into this journey to answer the question whether it makes sense to have optical switches inside the data center. So before we start, let's just have, oops, sorry. Stuck. Okay, so let's just have a look at how data center networks are built today. Now, I'm going to go very fast on this because I think it's probably known to most of you already. And also, I think Aslan did a very good job in the first talk to introducing this topic. So a typical cloud data center has about hundreds to thousands of racks, which are interconnected using optical fiber and electrical switches. So this is a great design, something that has served us very well. But also, as we are now approaching some of the more aggressive workloads, I think Tom was asking this question at the beginning. As we look at, for example, like massive distributed machine learning or memory disaggregation, there are some challenges that are start becoming potentially concerning. So the first one is that since the transmission is optical, but the switching is done electrically, effectively at every hop, we need to use power-hungry transceivers to convert from the optical to the digital domain. Second, once the packet is inside the switch, there is further delay that is added due to packet processing and queuing inside the switch. And finally, and I think Hitesh gave a very good explanation of this. So far, we have been happily riding the more slow, but as we are getting closer and closer to the end, there is also a question on how long we can actually sustain CMOS-based technology. And so the big question is whether there are alternative technologies that can help us in post-Moore era. So one of the technologies that we've been looking at that sounds very promising, at least on paper, is optical switch. So the advantages are relatively obvious. We don't need to use a transceiver, so we don't we can reduce the power consumption. Second, there are no processing inside the switch, so ultra low latency. In fact, we used to joke literally speed of light. And finally, we don't have a dependency on CMOS. And so potentially this could be the next curve that we can ride. So there are multiple ways in which you can build an optical switch. And again, I'm going fast on this because I think Hitesh explained this already. So the technology that we used is wavelength switching, which is based on two key components. The first one is called the AWGR. It's a passive component. There are no transistors or buffer. And you can think like a prism in the sense that it has this nice property that depending on the wavelength of the incoming signal, you will just redirect onto a different port. And so now I can combine this with a fast tunable laser, which as the name suggests, it's a laser that can tune very fast from one wavelength to another. And so, for example, if I want to talk to Francesca, I will tune my laser on red. And then if I want to talk to Hitesh, I can tune it on green. So we started this journey about 4 years ago. And the first question was, well, how fast can we tune this laser? So When we started in 2016, we were using off-the-shelf tunable lasers. These were tuning in about 1 millisecond. So this was the time for moving from one wavelength to another. And this in networking terms, it's a lifetime. So we spent really the first year in trying to really optimize this technology. And so we did optimization both at the electronics level, as well as we changed the way in which we were injecting current inside the lasers. And we were able to reduce the time to 100 nanoseconds. So on the one hand, this was a great result. Really, really like it was for those magnitude. So we were really, really excited. But deep down, we knew that this was not enough. And the reason is the following. If you consider some of these scenarios, which are characterized by very small packets, what you have is that, for example, if you take a 256 byte packet, so at 100 gig, it takes about 20 nanoseconds. So for example, if I want to send two packets back to back, let's say one to Francesca and one to Hitesh, ideally I would like to have something like this. On the other hand, if I have to wait 100 nanoseconds for my laser to tune, I end up with a massively underutilization, because most of the time I'm just going to sit idle without being able to transmit any packet. So this was the time in which we came to the realization that we fundamentally need to have a different approach in order to be able to achieve the nanosecond tuning speed that we were really after. So the main challenge with traditional tunable lasers is that the tuning section and the gain section are tightly coupled. And what this creates is that when you inject current in the tuning section, you also perturbate the gain section. And so this ultimately results in a longer tuning time. So our idea was to go for a disaggregated laser, effectively breaking up the lasers in two parts. One part that is responsible for multiple wavelengths, which is all to generate multiple wavelengths, which is in steady state, and then to have a wavelength selector that acts as a filter in order so that we can select the wavelength that we are interested in. And there are multiple ways to implement these ideas that we explore. And so one way was the one that Aslan presented today, using the comb as a way to generate multiple wavelengths. Another approach that we also experiment with was to use an array of lasers. So we design a chip where the first part of the chip is effectively a bank of lasers that act as a multi-wavelength source. And then in the second half of the chip, you have an array of SOAs that you can use effectively as a filter to select the wavelength that you're interested in. Switch this SOA on and off very fast. Effectively, we are able to achieve a sub-nanosecond tuning time, as also Aslan was showing today. And suddenly, effectively, what it means is that now our idle time between two subsequent transmissions becomes very, very small, to the point that it's practically negligible. So we designed this chip, we got it fabricated. We also package it so that we could integrate our prototype. And you may think that, okay, so pretty much we are close to the end. We have a strong motivation for optical switch. We have a functioning prototype that shows that we can achieve sub-nanosecond. So is job done? Not really. Because the fact is that there are still a number of challenges that you need to solve in order to go from the concept, just the optics device, to actually having a full system. So the main challenge is that fundamentally, the optical switch is not a drop-in replacement for electrical switch. And the reason is because they provide a very different abstraction. Optical switches are circuit switches, while instead electrical switches are packet switch. And this has implication across the entire stack. So not just in terms of the physical layer, but the entire stack is impacted by this change. So just to give you a feel of what are some of these challenges, the first one is about the clock and data recovery. So today, if you take like standard transceivers, they typically take about hundreds of nanoseconds, in some cases up to a microsecond, to lock onto the signal. And so this means that, sure, I can switch in 1 nanosecond, but then if it takes 100 nanoseconds before I can actually start processing data, basically my 1 nanosecond is completely useless because I'm bottlenecked on the CDR. So if you want to make nanosecond optical switching feasible, we also need to solve the problem of how we can achieve nanosecond level locking time for the CDR. And then next, the problem is about the scheduling. Optical switches are bufferless, so it means that we need to orchestrate, we need to schedule transmission, because otherwise we're going to have a lot of collisions. And so the question is, okay, how we can actually schedule at the scale of a cluster or a data center. And even if we are up working, we also need to have a mechanism to ensure that the clocks are synchronized, because it would be pointless to have a schedule that can operate at a tenth of nanosecond granularity, but then we have our clock that are completely unsynchronized. And then as we move up to the stack, the next problem is congestion control. If we just use TCP, the performance will be suboptimal. And so in a sense, we won't be able to fully utilize the benefits of having an optical switch. So what would be a congestion control design for optical switches? And finally, what's the impact on application? As we move from an asynchronous network to a synchronous network, how does this actually change for application? Can they benefit? Do we need to change them? Now, you might be tempted, since I was actually drawing this way, to think, well, just operate as an individual layer. So as an optics community, we take care only of the physical layer, and then people in the hardware community will take care of time synchronization and CDR, for example, and then networking folks are going to look into the congestion control, the schedule. And to some extent, this is what happened in many cases. But I think this would be a very big missed opportunity, because we believe, and this was actually the spirit behind the optics for the cloud group inside MSR, and in general about our initiative with the Optics for the Cloud, the Research Alliance, that in order to be able to efficiently and successfully solve these challenges, we really need to work as a group. That means effectively breaking the barriers across the layers, but also across community. So what we've been doing is trying to put together people with their very different background, optics, hardware, networking, and really work together, and also along our academic partners, in trying to address some of these challenges. Now, I don't have the time to really go in discussion one by one. Of course, we can more than happy to answer a question if you have, or we can discuss offline. But I just want to give you a glimpse of how we address some of these challenges in the context of the scheduling and the CDR, and hopefully show that there are benefits in also taking advantage, like leveraging the functionality provided by these different layers, and also of the unique position that you are when you operate inside the cloud, because there are a number of optimizations and a number of techniques that you can apply only if you are in the cloud. And we should really take advantage of this as we rethink of the stack. Scheduling is a very challenging problem, and there are multiple dimensions of it. The first dimension is actually how you compute the schedule. So you have effectively a matching problem in which you have potentially thousands or more of sources, to have thousands of destinations, and you effectively have to combine them. And you need to be able to achieve this, again, in a sub-microsecond scale in order to be able to be compatible with the speed of our switch. But it's not just about computing the schedule itself, it's also how do we collect all this demand? Do we need a separate network? What's the bandwidth? What's the latency requirement on this? Also, ideally, we don't want to wait for the packet to arrive into the NIC before we are actually able to send the request, because this will add additional latency. And if you remember, reducing latency was one of the key requirements for us. And so how can you actually estimate traffic demands? And finally, from a reliability perspective, so what happens, if or when, probably we should say, the scheduler fails, how we ensure continuity of operation, and so that we don't have a single point of failure in the network. Now, some of these questions can be solved. And in fact, for example, like the UCL team, I think, has done great work in addressing some of this. In our work, actually, we took a slightly different approach in which we try to explore this question. That is, can we actually build a network without a scheduler, or to be more precise, without a dynamic schedule? So the idea is that we employ a static, predefined schedule. So you can think of having a sequence of time slots, and the idea is that in every time slot, a node is communicating with another node. For example, here we have A is talking to B is talking to C, and so on. And then as the time moves on, then we just iterate in a round-robin fashion. So in the second slot, A is talking to C, B is talking to D, and so on. And so what it means is that when we reach the end, which what we call an epoch, every node will have communicate with all other nodes, and will have received packet from all the other nodes. Now, if we just use it like that, of course, it would be rather inefficient. And so we combine with an efficient routing system. People that are familiar is in a variant of bilateral balancing in order to be able to still maintain high throughput. Now, the advantage of using a scheduler-less network is on the one hand that we don't need a centralized entity and we don't need a separate control network. So fantastic. But there is also another advantage, and this is where the interlayer synergies start coming into the picture. Because now it means that, for example, the laser does not need to know packet by packet what is the next wavelength that it has to tune on. But effectively, we can predefine the schedule at bootstrap time. And then we don't need to have any communication between the laser and, for example, the transceiver. So this means that potentially you can even disaggregate the laser. The laser could actually sit somewhere else, and you just bring the light in, but you don't need to have any RF signal going from the transceiver to the laser, as an example. The case that I also want to discuss is a clock data recovery. So in today's network, as I was mentioning, it typically takes hundreds of nanoseconds, but it's not really a big deal because this is a price that you only pay at bootstrap time. So when you plug the cable, it will take some time before you can actually start transmitting packet, but you only do it once, and then you're fine because you keep on transmitting data. Instead, in an optical network, effectively every time you reconfigure the network, which in our case is every time we switch to a different wavelength, we are creating a new link. And so this means that at the physical layer, we need to require the clock of the source. And if this takes hundreds of nanoseconds, potentially can impact the throughput, because again, it would be time in which we are idle that we cannot transmit. So I don't want to say too much because tomorrow Kari is going to give a great talk about this, where he's going to describe in detail the exact mechanism we use. But I just want to give you the intuition of how this works, and especially how we can take advantage of the unique settings of Sirius and the cloud in general. So the idea is that for the CDR, typically you have to recover both the frequency and the phase. Now, since all the clocks are synchronized because we need them anyway to make the schedule work, it means that you don't need to recover the frequency. So already the problem is partly simplified. And second, since you are in a controlled environment like a data center, it means that also the phase is relatively stable. And so what you can do is that you can just measure it at the beginning, and then you can cache it and apply on your next transmission. And again, the fact that we have this cyclic communication helps a lot here, because what you can do is that periodically you can monitor this phase and you can adapt if you see that, for example, due to temperature is changing. And also, as we said for the lasers, since we already know in advance what the schedule will be, we can effectively preload this phase caching to ensure that the entire process works in a pipeline fashion. So if we now go back to our diagram, we can see how the scheduling, the specific scheduling that we chose, helped a lot in the design of the fast tunable laser. But also, as the time synchronization and the clock data recovery were instrumental, the scheduling and the time synchronization were instrumental to simplify the design of the clock data recovery. And unfortunately, I don't have the time, but similar things can also apply, for example, for time synchronization. The fact that we have a passive core with no retimers helps a lot, and congestion control and application. And so hopefully, you get this picture that by working together and by breaking these barriers across layers, we can really, really optimize the solution, because we are looking at an end-to-end system problem as opposed to an optimization of individual layers. So we take effectively these ideas and we implement in the prototype. So here is a paper that is coming up soon in case you want to know more information. But I also want to mention that it's still a long way to go, because there are still a lot of other challenges that we haven't solved yet. For example, reliability, management, deployment, create the ecosystem. And so it's important that when we think about moving from a concept to the actual deployment, we consider all of this as part of the research program. Now, I want to use still the last few minutes of my talk to also discuss another project on optical networks that we have in our group, and which is also went through a similar process. So this project is, Sirius was looking at the intra-data center, one instead Project Iris is actually looking at how we can actually optimize the regional network. So the region is effectively a collection of data centers that are connected with each other through a set of switches that are in the core of the region. And the region is defined in the order of 60 to 100 kilometers, where the idea there is that you want to have data centers that are relatively close to each other, about a few milliseconds of latency, but still far apart, so that if there is, for example, a fire in one data center, this will not affect all the other data centers. Now, again, this is a great design, and the fact that this is already in production for a few years now. But it also presents potentially some opportunities for improvement. For example, the fact that we have a lot of switches in the core clearly generates very high power consumption. Plus, also there is a problem because, for example, if we have two data centers that are close to each other, in principle, it would be nice to just go directly from one to another. But here we have always to route to the core of the region and then back, which adds a lot of latency. So the team has been looking at the question is that, well, can we use optical switches, different technology from the one that we have been using in our in series, but similar spirit as a way to reduce the power and also to enable more flexible topology that, for example, would allow to sort of shortcut between data centers that are in near proximity. You see this recurring theme across all the project that the concept seems relatively simple and say yes, sure, it should work. But once you start looking into it, you realize that there are a number of challenges, some related to optics and some related more in terms of management and control plane that need to be solved. And so the team has spent a lot of time in actually looking, for example, what's the best topology, also take into account physical constraints. How do we provision the capacity? How do we reconfigure the control plane? And also physical layer challenges, for example, amplifiers, that something that we didn't have in the context of series because we were short reach, but now in the regional start becoming important. And so they built a prototype, which we call the region in Iraq. And they also have a publication coming up soon. So I don't have time to really give you more details, but Thomas, Christos, and Francesca are on the line, so I'm sure that they're more than happy to answer any question that you can have. Okay, I reached the end. I hope Francesca is not too upset because I'm running a bit late. But I just, if you just want to remember one thing about this talk, is that as we look at this technology for the cloud, we really need to look at the system from an end-to-end perspective. So rather than thinking of the traditional individual layer, we really need to break these barriers. And also as a community, we really need to have a cross, interdisciplinary approach in which we take together people with different expertise and we work together in order to provide the best and most efficient solution for these problems. Okay, so thanks so much, and more than happy to take questions.
Thank you very much, Paolo. Are there any questions that you would like to ask Paolo or anyone at in the Microsoft team? Yeah, so Nicola Calabretta has a question. What is the link between edge and cloud?
Okay, very good question. When you define edge, are you talking about edge in the sense of like the regional, Nicola, or are you talking about the edge as actually, for example, point of presence of Azure inside providers?
Yeah, hi Paolo, hello, good afternoon to everybody. Sorry, I have some issue with the video, that's why I cannot. Yeah, I was thinking more about the point of, like you say, very close to the users. So because at the end of the story, the cost is mostly given by how many nodes you need to cross. So you would like to have an express channel, most probably from there to the cloud in case you need to go there or stay. But that is a perspective on operator. I'm curious to know what is the perspective of Microsoft.
It really depends on the workloads, because for example, there are workloads in which, so typically in data center, we used to think about east-west traffic and north-south. So east-west is the traffic that stays inside data center, and the north-south is the traffic that goes outside. And usually what happens is that the east-west traffic is orders of magnitude higher than the traffic that goes in and out. Just to give you an example, for example, think about when you do training for distributed machine learning, typically that's a lot of traffic within data center. Also, when you make, for example, a query in Bing, typically as a user, you just send a simple request. But inside, effectively, you have a number of microservices that are all connected with each other to give you the answer. So on the other hand, there could be other application, for example, streaming, in which in that case, of course, like, edge is more important, or also applications like, for example, virtual reality or gaming, in which in that case, you really want to have very, very low latency. And this is why, for example, like Azure and the same also some of the other cloud providers are actually having a lot of edge point in order to reduce the latency. So I guess yes, it really depends on the specific workload.
Yeah, indeed. Yeah, that's why I'm asking and curious, because it's probably you have a different application that typical operator will have. So that means also it's a different game. Also, what should be this age, or what actually reality is needed there compared to others? That's thank you very much, Paolo, for the answer.
Okay, thanks, Nicola.
Okay, I don't see any other questions, so I would, sorry, George Zervas has a question. What is the risk or rescheduleless control?
Yes, okay, thanks, George. So yes, the risk is that effectively you need to, in order to achieve the efficiency that you need to combine with routing protocol. And depending on the throughput, depending on the workload, in some cases, what you have to do is that you need to increase the bandwidth of some of the links in order to achieve, in order to be able to support the full workload. So it's a trade-off in terms of the kind of work that you have and the amount of bandwidth that you want to dedicate. Our analysis, however, show that even if you increase some of the bandwidth at the edge, you are still actually more cost-effective and also less power hungry compared to a traditional existing electrical switch solution.
If I understood correctly, sorry, Paul, you kind of pooling algorithm. You are considered scheduleless, or I'm trying to understand a bit better that one. Yeah.
So can you repeat your question?
Is a kind of pooling algorithm that something that you already make a kind of pooling already, that you just pre-assign a wavelength in order to avoid contention there?
Yes, in fact, it's a static schedule in which you have a deterministic schedule that ensures you have no contention.
Okay, so you are in a sense lose some flexibility in terms of that's why you need to increase the bandwidth in a sense to some extent.
It depends on the workload, because as I said, using this node balancing routing, you can still actually retain the same flexibility. On the other hand, depending on some of the workload, you may actually have to increase the bandwidth. But again, in the end, the net result is still positive. The net effect is still positive because you're actually, you're still moving all the transceivers in the core of the network.
Sure. Because otherwise you should have a control of thousands of transceiver, and that means your n log n or whatever algorithm you're making, you just lose all the advantage in terms of latency. Yeah. Exactly. Okay. That's we are working on a different approach is to do this, but that's the same problem. It need to be solved in some way, otherwise the sub-nanosecond switch doesn't help so much.
Exactly.
Yeah. Okay. Yeah. Thanks for the explanation.
So thank you very much. I think we are running out of time. So if you have any further question for Paolo or the Microsoft team, please write it in the meeting chat, and he or whoever will reply as soon as they can to their questions. So this brings me really to the closing remarks. I would like really to thank you all very much for joining us on the first day of our virtual optics for the cloud PhD event. As Ant and myself has mentioned at the beginning of the event, this has been our largest and virtual event so far that we ever organized, and I hope you agreed with me that this first day was a great success. I would like to thank Scarlett, Claire and Lynn for your very hard work in organizing it and running it so smoothly. I also would like to thank all the speakers, their supervisor, and actually all of you that have attended this event. Thank you very much for your question, and I would like to encourage you to continue being so proactive also for the event tomorrow. I personally enjoy very much to hear about the extremely interesting and exciting research that our academic collaborators are working on together with us. We truly appreciate how this current time may be very disruptive for many of you, so especially for PhD students. So it's really great to see the effort, your effort to continue in carrying out such a high level of research. I hope also you have enjoyed the update from our side with today's HeatEsh overview of our main projects in the optical space, followed by Paolo's deep dive into the networking side. And tomorrow there will be even more updates on our side. And these talks from Microsoft were arranged after the feedback that we received from you in a similar event last year. So I really, again, would like to encourage you to come back to us with any feedback that you may have about today and the event in general. It's really useful for us to receive any feedback that you may have. I'm looking forward to seeing you virtually again tomorrow for the second part of this very exciting event. We will have lots of other talks from our PhD students as well as from the Microsoft side.